And so you can see that as we lower this ramp down, how long is it going to take for this ball to roll up to this height if this angle is 0? For the 0 degree ramp, ball is just going to travel on with that maximum velocity that it had at the bottom forever and ever. Do you see that?
Yes.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
So lecture 29, titled Newton's First Law, Galileo's Principle of Inertia. So we're going to get to Newton's first law by talking about the work that Galileo did, which preceded Newton's work. And yeah, notice I'm sure with an inclined plane. But also we're going to be talking about inclined planes. So this is how Galileo made his measurements, by rolling marbles down inclined planes. And so what I've drawn here is an inclined plane. Do you understand the concept of it? Yeah, it's a little hill. It's got a constant slope, and you roll a little marble down it. Now, why would you do that? Well, because when you drop things, it all happens very quickly, and it's hard to make accurate measurements of what's going on with the motion of that object. If I drop a marble, it's the same as when I drop a pen. So instead, if you roll them down an inclined plane, then based on what the angle of inclination is, right, the lower that is, the slower the acceleration. We already know about acceleration because we talked about it in kinematics. So you can kind of tune the acceleration you get by changing the angle of incline. So in general, we can think of, here's the ball, and we of course have an acceleration straight down of minus g, 32 feet per second, 10 meters per second, whatever you want to think of it as. But we can't travel straight down. To get down, we have to go this way. And so we can break up the acceleration into two components. One that is perpendicular. If you think of this as this big triangle, this is the hypotenuse. We could also call that our track length. So our track length is also the hypotenuse of this larger triangle I've drawn with angle theta. And I can think of two components of the acceleration. One that is perpendicular to this track length.
Yes.
And so what is you can see that there is no acceleration in the perpendicular direction. It is not moving down this way at all. All of its motion is in this direction, which is the acceleration parallel to the track length, or the hypotenuse. You see?
Yes.
Well, because this green line, the perpendicular component of the acceleration, is perpendicular to this track length line, and this blue line I've drawn here, the parallel acceleration component, is parallel to it. The angle subtended by these two, and because the direction of the gravitational acceleration, which is straight down, is parallel to this side over here, right? Which I haven't really drawn anything on, but I'll put a little tick mark there. They're not equal, but they're parallel. So the angle theta here is the same as the angle theta here. Okay, it's a similar triangles relationship, and it's just because the green line is perpendicular to this, the blue line is parallel to this, and the hypotenuse of this larger triangle is parallel to this side. So that means that we can write these components as follows. The perpendicular component of acceleration is just 0. There is no acceleration in this direction. All the acceleration is in this direction. And so A parallel is equal to minus g times the sine of theta. Because if this is theta, the sine of theta is the opposite over the adjacent. So if I take the opposite over the hypotenuse here is minus g. So if I take minus g and multiply it times the sine of theta, I get this component A parallel. So that's how you might recall that the sine of theta can vary between 0 and 1. So if we can make the sine of theta 0, we can completely turn off all acceleration. And so that, of course, would correspond to, this angle being all the way down like this. So it's a flat inclined plane, right? It's just going to sit there. Whereas if we raise it all the way up to 90 degrees, that's making this angle go all the way up like that. That's just the marble falling straight down. So if the angle theta is 90 degrees, then the marble just falls straight down. You get the full acceleration due to gravity. So we, of course, want to be somewhere in between those two extremes. Usually, because the reason you're doing this is to kind of slow down this acceleration so you don't get so fast so quickly. So it's worthwhile to mention the small angle approximation. The small angle approximation is basically this. I'm not going to prove it, but I'll just show you. The sine of theta is approximately equal to theta for small angles.
Okay.
Now, this is in radians, though. It does not work in degrees. And so to do it in degrees, we would have to say something like, if you want it in degrees, you have to multiply this number here, right? If you specify theta in degrees, then you have to multiply it times pi over 180 to convert it from degrees into radians.
Okay.
So if we wanted to, for example, consider what is the what's the acceleration we would see on an inclined plane if we used theta of 10 degrees?
Yes.
Well, so if I do A parallel for 10 degrees, that's going to be minus g times the sine of theta we're going to replace with theta. But since I'm specifying this in degrees, I'm going to make sure I put my conversion factor from degrees into radians. And so that's pi over 180 degrees, which gives me minus g times pi over 18. And pi is, about 3, and so we can approximate this as approximately minus g over 6, right? Because 6 times 3 is 18.
Okay.
Yeah, so it allows you to turn the acceleration from gravity into 1/6 that value at a 10-degree incline.
Mm-hmm.
So things would be moving much slower, be much more easy to make those measurements. I put a homework assignment. In the homework assignment, there'll be one problem that has to do with inclined planes and it has to do with bells. So because things were hard to time, Galileo had a clever idea, right? He observed that, well, we're not really good at making accurate time measurements, but our brain is really good at recognizing a steady beat. If you ever listen to a band or a drummer that can't keep the beat, it just doesn't sound right. And you see it. Our brain is really good at picking up any variation in that. And so if he were to set up some bells along the track of the inclined plane, such that as the ball rolled through, it rang one of those bells, he could get the spacing of those bells such that it was a nice, steady beat. Okay? And then from that, you can backtrack a lot of information. You know those are equal time intervals, right?
Yeah.
If you're getting a steady beat, that means that wherever the bells are, that corresponds to a distance at which the ball has traversed an equal time interval. And so in this homework assignment, you'll be able to think about that and how you would place the bells so that you would get an equal time interval.
If there's bells, would you turn it into that slow it down?
Well, of course. And it has to be a very, you have to make it a small effect. Right? So it'd be like a little, maybe a paper clip, but you could have a little paper clip such that as the ball went by, it just touched it. And so it just caused the paper clip to wiggle a bell so it would ring. So it's not going to be terribly loud. Yes, you're going to lose some of its energy, right, as you ring those bells going down, but you can minimize that and it will have a negligible effect on your results. This is the inclined plane. This is how it works. It just allows us to decrease the acceleration that the ball experiences so that we can make more accurate measurements of its motion. And we talked about this kind of motion, constant acceleration, body experiencing constant acceleration in some detail when we did kinematics.
Okay.
So I'm not going to really do much more of that. But I do want to consider the following. It's very likely when doing these experiments that you could construct 2 ramps. And if you did, we'll call this ramp 1 and this ramp 2. And if we drop this ball from, say, a height h, it's going to roll down. We'll assume these corners are kind of smooth. And it's going to go back up. We're going to observe that it basically rises back up to the same height. Now it'll be a little bit less because there's energy that's being lost, but we haven't talked about energy yet, so we can't really talk about that. But in an ideal world, if the surfaces are frictionless, if these corners are perfectly smooth, then this ball will roll down this first incline through this flat section and then back up this incline until it gets to the same height as before. And then, of course, it'll roll back down. And if it's completely frictionless and there's no air resistance or anything, it'll just do that forever. But I don't want to worry about that part of it. I just want to worry about the idea that if I let this ball roll down, it's going to roll back up to the same height as before. Does that make sense to everybody?
Yes.
Yes? Well, what would happen if and here maybe we say that the angle of this incline here is the same. So these are the same angles. But now let this second angle be less. Let's make it something like this. We have the first incline, the straight flat section, and then I'm going to actually draw the second ramp in a different color so that we know where it's at. This time, I'm going to let this ramp have a pretty shallow angle compared to what it did before. And so, if I start the ball out at this height h, I know from my previous observations with these things that it's going to roll down this ramp until it gets to this point right here, right? Because this is the distance h across. Draw that in there. We know it's going to roll up to here, yes? Before it rolls back. So you can kind of see that as, let's call this one phi, and this original angle was beta. As I let this second ramp angle get lower and lower and lower, you can see that this point is going to move farther and farther away. So let me consider another angle in the same picture. This time, I'm going to choose it to be this. And again, I have to get, the ball is going to have to travel far enough in the x direction, or the horizontal direction, to get to that point right there, yes?
Yes.
And so you can see that as I keep decreasing this angle, I just want to kind of consider this limit, right? I'll make it just a wee bit less than what I want to consider here. That's even lower. And so you can see that well, the ball is going to roll for a very, very long time, right?
Yes.
Now I should point out that just by symmetry here, right? If at this point the ball is moving at 0 meters per second, here when it turns around it'll be going 0 meters per second, yes?
Yes.
It'll have some maximum speed at the bottom.
Yes.
That's when the acceleration stops. Now it's got no more acceleration because it's in this flat section, yes?
Yes.
So whatever its speed is, that's what it's going to have there. So that'll be its maximum speed. And we can figure that if this, because of time symmetry, right, its maximum speed will be the same here at the beginning of this ramp. Which means that during this whole period here, we'll just call it Vmax. And so you can see that as we lower this ramp down, how long is it going to take for this ball to roll up to this height if this angle is 0? For the 0 degree ramp, ball is just going to travel on with that maximum velocity that it had at the bottom forever and ever.
Yes.
Do you see that?
Yes. No resistance or friction.
No friction. We're assuming there's 0 friction. And so this ball is going to roll on forever and ever.
Okay.
But see, this is I don't know for a fact that this is how Galileo figured it out. Because we have the benefit of having seen, space movies and stuff. Right? So we know that if we were like in outer space or orbiting around the Earth, right, where Earth's gravity is canceled out because we're falling, that if I take a pen and I toss it to you, it'll just keep going in the direction that I toss it forever and ever until somebody catches it.
Okay.
If you saw that, what was it called? The Sandra Bullock movie, Gravity, I think?
Yes.
And the guy, he got away from the spaceship and he's floating out, right? I mean, it was a real problem because if he didn't have a way to, some thrusters or something to get back, then he's just going to float out in space forever.
Yes.
Because that's how things work in space. If there's no gravity around you, then you're just going to keep traveling on at whatever speed you happen to be at.
Okay.
But Galileo wouldn't have had any of that, movie insight because he wouldn't have seen any of those movies.
All right.
So, the prevailing view at the time was Aristotle, who tried to explain why things move. He thought that motion was like the natural state of things.
Yes.
Whereas Galileo discovered it's really the change in that's important. So in this case here, when phi is equal to 0 degrees, delta v is equal to 0. So what does that mean? That means that the velocity never changes.
Okay.
And so this is the principle of inertia. It's the idea that an isolated object with velocity v does not accelerate. Well, that's one way to say it. It doesn't matter what the velocity is. If the velocity is 0, it's going to stay 0. If the velocity is some other number, maybe this maximum velocity we got at the end of our ramp, in our inclined plane, then it'll stay at that velocity forever.
Okay.
And so this is how you can kind of see that coming about. Just by making this observation that when you roll this thing, it'll roll back up until it gets to this height. Now, he doesn't know why that is. We'll understand why that is. We'll talk about that. I don't want to jump to that too soon, so I'm not going to explain why that is. But it's something that you can observe. It's a little bit like when you bounce a basketball. If you bounce a basketball and you threw it to the ground and it went, really, really high, you'd be like, well, that's not supposed to happen. Or if you tried to bounce it and it only bounced like a centimeter, you'd be like, well, that's not how it's supposed to happen. You expect it. If you take the ball and you drop it, at most it's going to bounce back up to the height that you dropped it from.
Yes.
If it bounced higher, you know that maybe you gave it too much, you gave it a push or something, who knows? It just doesn't seem right. But this idea of things, inclined planes, balls rolling, and then rolling back up to the same height, and then they stop, makes sense to us. If we change this angle, then it takes a longer time before it reaches that height.
Yes.
Because this distance is increasing. And if the angle is 0, now the distance to get back up to that height is infinity, which means it's never going to get there, which means that its velocity will stay unchanged. And this is the idea behind the principle of inertia.
Okay.
Other aspects of inertia we'll talk about in the next lecture when we talk about Newton's second law.
All right.
Because there's another idea associated with inertia in that, what we would call a heavy object is it's hard to change its state of motion. If you have a big boulder, it's much harder to roll that off a hill than it is a little tiny pebble.
Yes.
So, but I don't want to get into mass yet. And that does have to do with mass. They would have thought of, weight or weightiness. They didn't have these formal definitions back then, so they wouldn't have distinguished between weight and mass like we do today. But again, that's getting ahead of ourselves. This is really all I wanted to focus on now, is this idea that isolated objects, meaning there are no interactions, there's no ramp to climb, right? There's nothing to bump into, maintain their state of motion. That's the natural state of it. If something is moving, it will just keep on moving. If something is staying still, it'll keep on staying still. And of course, we have to throw in reference frames here. You always have to remember everything is relative. So you have to think about what reference frame you mean that by.
Okay.
But within the same reference frame, the laws of inertia, or the principle of inertia holds. Okay, that's it. Here we are, lecture 30, titled Force is the Strength of an Interaction. So obviously we'll be talking about force. The next lecture we do, lecture 31, will be specifically on Newton's laws. Right, the last lecture we did, we kind of motivated the law of, or the principle of inertia, which will be stated in Newton's first law. And today we're going to motivate his other two laws, the second and the third law. But we're not really going to talk about Newton's laws in particular. Instead, we're going to talk about what I like to call ice-rink physics. So, you know what an ice rink is?
Yes.
Ice rink is where you go to skate. And if you've ever skated, you know that it's relatively frictionless. And so if two people go out into the middle of an ice rink and one of them pushes the other, what's going to happen?
They'll start going forward for this.
Let's assume they don't fall over, right? It's not an aggressive mean push. What's going to happen? Let's say these are the two ice skaters and they're in the middle of the ice rink. If this guy pushes on this guy, what happens?
It's going to start sliding.
Who is?
The guy.
So you're saying that if this guy pushes on this guy, it's going to go like this?
No, they're both going to go.
Ah, very good. Yeah, so if this guy pushes on this guy, they're going to go like this, right?
Yeah.
Yeah. Okay, so that's important to note. So we've got a couple of friends. We'll call them Alex and Bartleby.
All right.
Alex and Bartleby, A and B, go in the ice rink. They decide to have a little push-off competition. And so a bystander is going to observe these pushes that they're doing and going to make measurements. Okay, and they're going to, in particular, measure their velocity. Now, before, they weren't moving. Afterwards, as you can see, right, depending on which way they push, you can find a line in which the motion will take place in, and so you can really think of this as kind of a one-dimensional problem. If they decide to push this way, here's the line. The line goes like this. So we may have to reorient our line, but we can find a line, right, where the motion is basically one-dimensional. And if you know that initially they were not moving, so their velocity is 0, and then after they push off, you'll measure what their velocities are.
Okay.
And maybe you're very careful to observe how long they're actually touching.
Yes.
And that'll be some time period, delta t. And if we take delta v and divide it by delta t, what do we get? What do we call this quantity? Delta v divided by delta t. That's the change in the velocity divided by the change in the time.
It's, acceleration.
That's acceleration, of course. So our observer is keeping track of the acceleration. So these guys tried, this pushing competition, and we recorded the following data. So in the first experiment, you can see it over here on the monitor. A had an I have a printout of it here. I can just read from that instead. A had an acceleration of -2, and B had an acceleration of 1. Now why the -2? Why is it negative? Anybody?
Going in the negative direction.
Well, more importantly, they're going in opposite directions, right? When they push off of each other, one will go one way, one will go the complete opposite direction.
Okay.
That's where the negative comes from. So apparently B is accelerating in the positive direction in all 5 of these experiments. So we had the acceleration of A is -2. Maybe it's meters per second squared, it's feet per second squared, whatever, right? Not worried about units. And the acceleration of B was just 1. In the second experiment, B had an acceleration of 2, and A had an acceleration of -4. In the next one, B had an acceleration of 3, whereas A had an acceleration of -6. And then the next one, B had an acceleration of 4, and A had an acceleration of minus 8. And in the final experiment, B had an acceleration of 5, and A had an acceleration of minus 10. Now, you've already noticed that these accelerations have opposite signs, which makes sense since they're moving in opposite directions. But what else do you notice about the data that I put up on the board here? Anything that pops out to you? I will point out that B is a little bit bigger than A. That's why I used a font size for B that was just a little bit bigger than font size of A, to show you that A and B are of different sizes. So we might have A is like this and B is a little bit bigger. All right, experiment number 1. Acceleration of B is 1, acceleration of A is minus 2. That's how you read it, okay?
Okay.
So I'm writing the acceleration as A for acceleration, and then in the subscript I'll either put an A or a B, right? So that's the acceleration of A.
Okay.
Does anything about this data pop out to you?
The A has a greater acceleration than B.
In all cases?
Yeah. Yes, it's twice as much. Except
Twice as much, yeah, interesting. So what if I were to take the ratio of, say, the acceleration of B divided by the acceleration of A? Right, in the first case, I would get 1 over minus 2, that's minus a half. In the second experiment, I would get 2 over minus 4, but that reduces to minus a half. In the third experiment, I would get 3 over minus 6, which is also going to reduce to minus a half. In the next experiment, I would get 4 over minus 8, which is minus a half. You see where this is going. It seems that the ratio of their accelerations is negative.
Yeah.
That reflects the fact that they're moving in opposite directions or accelerating in opposite directions. And a constant value, it doesn't change. The numbers themselves in the numerator and denominator may be different, but they reduce to the same ratio, a constant.
Okay.
So, given that this happens, A and B decided to get 3 other friends to come in, arrange to have their other friends, ranging in weight or size of the weest Alex, or A, to the heftiest Egbert, or E, as it's labeled here. I also tried to get the fonts to reflect their relative size. So here, E is very big, we say.
Yeah.
A is very small. And they're going to do these pushing experiments again. But they want to pair up. And how many different pairs can we come up with if we have 5 people that we might want to pair up? Anyone know how to answer that question?
5 plus 4 plus 3 plus 2 plus 1.
Well, actually, it is. But there's an easier way to think of it, right? If you're going to try to catalog all these interactions, think of a multiplication table. That's what I've drawn up here. And so in each column, you label them with the people, A through E.
Okay.
And this intersection with this diagonal in the middle there, that would be A and A paired up. Well, that doesn't make any sense. You can't pair a person up with himself. So the diagonal should not be included. This line here would be A paired up with B. This would be A paired up with C. You see how it's working, right?
Yes.
A with D, A with E. But on the other side of the diagonal, we have A paired up with B, but over here we have B paired up with A. And we already said we're not going to count that twice. So the only relevant entries in the table here are this little triangle here, right? And that's why it's 5 plus 4 plus 3 plus 2, because this is basically Gauss's counting problem. In the end, though, it's whether we have 5 factorial over 3 factorial times 2 factorial, or we just count up the entries in this side of the triangle. We get 10 if we have 5 friends. Okay, so we're going to pair them all up, and then we're going to do an experiment and see what these accelerations are. So, but I just want to point out that these entries here, what we're going to see are the accelerations of, say, C and the accelerations of D in their experiment in this block right here. You see that the row number is the first letter, the column number is the second letter, right?
Yeah.
So this represents the pairing of C and D.
Okay.
And so here we have the experimental results. So when we paired A up with B, we saw that B had an acceleration of 1, A had an acceleration of minus 2, very similar to one of the experimental data points we had in the first experiment, where it just involved A and B pushing at various strengths.
Yes.
And you might recall that when they were pushing, the ratio was the same of their accelerations, regardless of how hard they push. Yes?
Yes.
Didn't matter. Always came out the same. So here we're pairing up different individuals. And they're all of different sizes, right? A is the weest, E is the heftiest.
Okay.
And so we look at these pairings and the accelerations, and nothing magical really pops out to us. We use the insight from the first experiment, where we said, well, let's look at the ratios and see what that does for us. And so now we get these ratios. We see that and I'm writing this term, alpha sub BA, for example. That means the ratio of the accelerations, B divided by A. So it's the ratio of the acceleration of B to the acceleration of A. And that's what we get here. So if I said alpha CA, that would be the acceleration of C divided by the acceleration of A. And we find that that's equal to minus 1/3.
Okay.
So here we have all these numbers for all of these different people. So let's look at a specific interaction. Let's look at the first one, the alpha beta A, alpha BA. So what is this saying? This is saying that the acceleration of A is equal to twice the acceleration of B.
Yeah.
The sign difference, of course, is again reflecting the fact that they're pushing away. We could also look at alpha, let's look at EA. So now we're comparing the weakest with the heftiest. And so this, again, is equal to the acceleration of E divided by the acceleration of A. And that we found was equal to minus 1/5, which means that the acceleration of A is 5 times that experienced by E. And that kind of makes sense, right? If we've got the really big fella here and the little fella here, and the big fella gives a push, big fella's going to move away pretty slowly, but the little guy is going to fly off pretty quickly.
Yes.
So that kind of makes sense. The heftier ones, the larger ones, the weightier ones, whatever you want to call it, accelerate less, and the others accelerate more. And so we can kind of think of this ratio, if we wanted to, we can say, well, it's kind of like we have this movability index that we could imagine as follows. And I'll call the movability N, and we'll put a subscript on it to indicate which object we're referring to, whether it's A or B or C or D. And so any of these alpha ij, where I and j are any index, is equal to Ni over Nj. So we're saying the ratio of the accelerations is proportional to the ratio of the movabilities.
Yes.
So, E is less movable than A is. Again, these are ratios, so you can't just automatically pull out their absolute, magnitudes from one ratio. So I cannot definitively say that the movability of E is 1 and the movability of A is 5. What I can say is that if the movability of E is 1, then the movability of A would be 5.
Yes.
Because the movability of A is 5 times greater than the movability of E, because A is smaller.
Yes.
So now, I also want to look at alpha EA. So using these definitions, right, that I gave, the ratio of the accelerations being equal to the ratio of the movabilities, right? For BA, it's NB over NA, and for the ratio of the accelerations for EA would be the ratio of the movabilities N sub E, which is the movability of E, over N sub B, the movability of B. Oh wait, that should be an A. Sorry. Yeah, BA and EA. Good. What I'd like to do with this, and I may need a little more room, I want to predict what is the ratio of the accelerations for E and B. And we know that by this definition, that would be the ratio of the movability of E divided by the movability of B, which I can rewrite as NE over NA times NA over NB. This should start to remind you of the last thing we did with geometrical optics when we talked about the principle of least time and predicting the index of refraction, right? Remember that? That was just 2 lessons ago. So this is the same thing as N sub E. You see why this is true, because the N sub A's cancel. I'm left with N sub E over N sub B. This is N sub E over N sub A divided by N sub B over N sub A, just because of the way that fractions divide. And this now is equal to, well, N sub E over N sub A, that's just alpha EA. Divided by, that means this, NB over NA, right, that is just alpha BA. These two values that we measured, you see?
Yeah.
And so this says that we can predict the ratio of the accelerations for E and B from the values for E and A and B and A, right? And we have those values in our table. Let's see if it matches up with the experimental data we have over here. So alpha EA, what is it? Can somebody read it from the data over there? What does that equal to?
Minus 1/5.
Yes, that's 1/5, right? I'm going to ignore the signs because the signs can throw things off. I actually had some trouble with this when I was thinking about this lecture. The signs can mess things up a little bit. So we'll just remember that whatever this is, it's going to be negative, okay? And I'm not going to worry about the signs. So I'll say that's 1/5, right? And we're going to divide that by alpha BA. What's alpha BA?
That's negative 1/2.
Yes, that's a half. Which if I divide by half, it's the same thing as multiplying by 2 over 1. So that tells me that I predict that alpha EB will be equal to minus 2 over 5. And does that agree with the experimental results we have in the table?
Yes, it does.
It's exactly the same as what we observed experimentally. See? So we were able to predict the interaction between E and B based on the interaction between A and B and E and A.
Okay.
So let me suggest what this movability number is, right? Again, it's a number that tells you how movable something is. If something has a very high movability, it's easy to move. If something has a very low movability, it's hard to move. Now let me just suggest that what this is the mass.
All right.
So the mass of A will be equal to 1 over the mass of A, 1 over the movability of A.
Okay.
And we could, if we wanted to come up with a dynamical definition of mass in terms of the ratio of accelerations using this,
Yes.
you need to pick like a standard. You say, okay, well, I'm going to use my basis for mass measurements. I'm going to maybe make it the kilogram, and I'll let A be an object that has a mass of 1 kilogram, and then I could write out the mass of any other object in the universe by simply using these ratios of accelerations,
Okay.
and that would work fine. But I'm not going to worry about that too much. I'm just going to point out that this movability is really, it's the inverse. The inverse of the movability is the mass, and that makes sense, because a heavy object is hard to move. Big, massive object,
All right.
not easy to move. So 1 over a big number will be a very small number.
Yes.
So it'll have a low movability. Whereas a really light object is easy to move. It should have a high movability. If I have a teeny tiny object, something that weighs, 0.0000001 kilograms, it's going to have a very big movability because 1 over a really tiny number is a really big number.
Yes.
So mass is 1 over this movability. This suggests that the strength of each interaction, these are all interactions. I've been careful not to use the word force. I may have said push or something like that, but these are interactions. I'm not going to go into any detail about what's happening. I don't really care. In the time that they're touching, all I know is that they're accelerating because they started at 0 velocity, and after they touched for some period of time, they came out with a higher velocity. And so this interaction, I'm going to suggest that the strength of this interaction, and we can define the strength of interaction, AI over NI, which is the same thing as MI times AI. So I is just a particular element. It could be the mass of A and the acceleration of A,
Yes.
which I'm going to call force.
Okay. All right.
So this, what we see in here, this combination of terms, the acceleration divided by the movability, or the mass times the acceleration, is the strength of this interaction. We call that strength the force. And this, essentially, we're going to come and find is basically Newton's second law, which we'll go to more. We'll go more into tomorrow. So if we substitute these new terms into what we've been doing here with these interactions, right? We have the so a sub I, the acceleration of I, divided by the acceleration of j. This would be equal to the movability of I over the movability of j, as we were using before. But remember that I'm defining mass as the inverse of movability, so that means that this is also equal to m sub j over m sub I. The indexes switch places, you see? Well, this suggests that m sub I times a sub I is equal to minus m sub j times a sub j. And this will turn out to be Newton's third law. There's only one interaction,
Okay.
and it only really has one strength, but you can see there's this kind of reciprocal relationship that the force on one is equal and opposite to the force on the other, you see?
Yes.
And we'll talk about that and kind of the traditional discussion of Newton's laws in the next lesson. But for now, this is just a motivation for why all of this is the way it is.
Okay.
And so based on these, kind of pseudo experimental results, right? I didn't really go into an ice rink and do these experiments, but if I did, these are the numbers I'd get.
Okay.
If the players have the masses that I use to generate these results. Okay, any questions on that? We're going to talk about Newton's second law in a little more detail, in a more traditional way. We're actually going to begin by talking about what Newton described as the quantity of motion. And the quantity of motion is what we now call momentum. It's represented by the symbol P, and it's equal to the mass times the velocity. Now, of course, since velocity is a vector, so is momentum. This definition of quantity of momentum kind of makes sense, because if you think of the difference between, a very light object that's moving at a constant velocity, like a bicycle that's moving down the road at 25 miles per hour,
yeah,
that has a different quantity of motion than, say, a car traveling down the road at a constant velocity of 25 miles per hour, right? Because clearly you would rather be hit by the bicycle than the car.
yes.
And so there must be something about its state of motion which made you come to that decision.
Mm-hmm.
Yes. So this was Newton's definition. Now, if the change in the momentum is not equal to 0, then this means that there was some interaction. This is my symbol for implies. So if there's no change, if there is a change in the momentum, then that implies there's some kind of interaction. And this, of course, is what we talk about as force. So you say, well, if there's a change in the momentum, then there's a force. Now remember, Aristotle, 1,000 years before Newton, or more like 2,000 years before Newton, would have said, when he thought about motion, he would ask the question, what makes something move? Or really more accurately, what keeps something moving? Because in his world, right, if you were to, put a bicycle into motion, eventually it would come to rest. And so he'd think, well, what do you have to do to keep it moving? So if he had a definition of force, he would think it is the thing that kept the bike moving down the road. Whereas Newton is interested in what creates a change in the state of motion. Remember, the first law, it was basically that said that in the absence of an interaction of some kind, or in the absence of any external forces, there's no change in the momentum. If you're sitting still, you continue to sit still. If you're moving with a constant velocity, you continue to move with a constant velocity. This is this principle of inertia that originated with Galileo.
Mm-hmm.
So we can now say that the force is the time rate of change of momentum.
Okay.
And if I use this definition up here for momentum and consider constant mass. So if the mass is not changing, then this is just m times delta v over delta t, which is just m times delta v over delta t. And who knows what delta v over delta t is?
Acceleration.
Acceleration. So this is mass times acceleration, which makes force, of course, a vector quantity. And experimentally, we observe that force is a vector quantity.
Okay.
Now, I've got a series of questions I want to ask along the way here. So, if the acceleration on a body is 0, are there any forces?
No.
Well, maybe I jumped the gun here. Hold off on that question because I need to add one more thing to this. I'm going to formally state that Newton's second law, what's called N2, basically says that acceleration is equal to the sum, this Greek sigma, uppercase sigma, we use to stand for sum. It means you add them up, of the forces, and inversely proportional to the mass. And these are vectors. Sometimes you can call that net force. So remember, forces are a vector quantity. If forces are a vector quantity, that means they have direction and magnitude.
Yes.
And so they will add by the parallelogram rule of addition.
Okay.
Yeah, remember the parallelogram rule of addition? This is a force 1, and then I have another force in this direction, right? And we can think of this parallelogram. And the sum of these two bisects this parallelogram. That's a parabol. So this is F1 plus F2, right? So another way to think about it is that force, adding like a vector, right, will add we can add the components.
Okay.
So if you put a coordinate system on there, you can break it down into components. You can say, well, here's the force in the x direction, here's the force in the y direction, and then you can express the force in terms of those components. And if you add two forces, their components will add. So now I ask the question. If the acceleration is 0, does that mean that there are no forces? Any ideas?
Okay.
Well, let's just work it through. If we say acceleration is 0, that means that the sum of the forces divided by mass, I can just multiply both sides by the mass, and anything times 0 is still 0, so we get that the sum of the forces is equal to 0. That's different than saying that there are no forces, because forces are a vector quantity. They can add in a way, right? Here's F1, here is F2. They're going in opposite directions.
Yes.
Let's say that their magnitudes are equal.
Okay.
The sum of those two forces is 0.
Okay. All right.
You can think of this as, a tug of war between two people that are pulling with exactly the same amount of force. Not going to move one way or the other. It's just going to stand still.
Okay.
Okay, so I want to quantify force, and so we have to define it. And since Newton invented it, it's named after him. And so the unit of force is called a Newton. And we define 1 Newton as the amount of force. Right, so let me just... It's the amount of force to accelerate a 1 kilogram body 1 meter per second per second.
Okay.
That's 1 Newton. So 1 Newton equals 1 kilogram times 1 meter per second squared. That is the definition of a Newton, and that is our unit of force.
Okay.
Now, that being said, we need a way to actually measure these forces, and I'm going to erase this. I don't think we need this anymore. And a good way to measure forces is with a spring. And so you'll find that with a spring, it'll have a relaxed state.
Okay.
I'm going to consider this a wall. So here the spring is in a relaxed state. If I pull on the string, I'll call this position, the position of the end here, I'll call this position x naught, and I'll call this position x, and this is not x, this is delta x, or the displacement. So if I pull on a spring, it stretches out. So this point here at the end is now at a new position x, and so delta x is equal to x minus x naught.
Okay.
It's the amount from equilibrium that we stretch it out to. Okay, it's how much we change the length of the spring, I guess you could say. Make sense?
Yes.
It would also work for compression. You could compress it, squish it, and however far to the left you went, x naught minus that would be your delta x. And so you can plot. You will find, and this is called Hooke's law, you will find that for a large region, or for large displacements up to some point, that Hooke's law is linear,
All right.
which means that the force that you get is proportional to the displacement of the spring.
All right.
And so with that, we can now imagine a force measuring device. If I place a block of some mass m on a frictionless table, I can attach it to this kind of spring scale. Right? This will have a spring inside of it, and over here I'll have an end that I can pull, apply a force, and it will have a gauge on it with tick marks all the way through. And as I pull on this, I'll have a little indicator which shows me how much the spring is stretched from equilibrium. Okay, and I can measure that. So I can use this thing to measure force. I can first calibrate it by using, set this to be a 1 kilogram block. Now all I have to do is accelerate it to 1 meter per second per second.
Yep.
And whatever I read on there will be 1 Newton.
Okay.
And so now it's calibrated. And thereafter, I can put any mass on there that I want. And I can pull on it, and I can measure how much force I am applying to it.
Okay.
If I know the acceleration, then I can determine the mass. If I know the mass, then I can determine the acceleration.
All right.
So this is a useful way to measure stuff. And now we can define what mass is. And we'll do this with this dynamical definition of mass. Right? So I'll say mass defined. I'm going to say that the mass of something, this will turn out to be, remember alpha from yesterday?
Yes.
Okay, so M naught and A naught, these are my standards, okay? This is my 1 kilogram block, for example, right? So all I need to do is, just like we did yesterday, or in the last lesson, is measure the ratio of the accelerations, right, using a standard mass, and I can write any mass in terms of that. And further, A naught times M naught is F naught. That's my standard force, 1 Newton. And so now all I need to do is measure the acceleration when I apply a 1 Newton force, which I can do with my calibrated spring, and that will determine the mass.
Okay.
So does that make sense?
Yes.
Can you judge mass by size? If I look at something, here's a big thing, here's a smaller thing, and I look at it and go, oh, well, that thing, the bigger thing, has definitely got a bigger mass.
No.
No, you cannot. Because how do we determine what mass is? Right?
Yes.
We apply a standard force of 1 Newton, we see what the acceleration is. That's how we figure out what mass is.
Okay.
Can mass be negative?
No.
In terms of this dynamical definition, right, I think you can see that you cannot have negative mass. That would be like having, when we had the two bodies pushing on each other yesterday, or in the last lesson,
Yes.
right? If two people push off on the ice rink and they end up both going in the same direction, does that make any sense? Would that ever happen? Well, that's what it would look like to have a negative mass. What about the idea that mass is defined as a quantity of matter? You've probably heard this discussion before, or heard this line of reasoning before, that mass is a measure of the quantity of matter.
Mm-hmm.
How does that compare with our definition of mass? Right? Any thoughts on that?
Less accurate?
Well,
Entirely true.
in order for that to work, you would have to have some smallest mass that everything else is defined in terms of.
Yeah.
And so you've studied chemistry, so you know that atoms are small things, and they're made up of protons, neutrons, and electrons.
Yes.
So you can say, okay, well, if we add up the protons, neutrons, and electrons, then we should be able to get the total mass of the thing if we know how many of each of those things is in the matter that's present.
Right.
And so in that respect, it differs in that we have to know what's at the bottom. What are the things that make up the matter that we have to add up, right? When we get this quantity of matter, that means how many protons, how many neutrons, how many electrons. So we need to know that. Do we need to know any of that detail to use this definition of mass? No, we do not.
No.
That's why I call it a dynamical definition of mass.
Okay.
As opposed, I guess you could call the other one a static definition of mass, where we say it's the sum of the protons, the neutrons, and the electrons. And that would be, a valid way to do things. There is a complication that arises that Einstein gives us that makes it not possible to actually use that to accurately measure mass. Turns out that you can have the same number of protons, neutrons, and electrons in some composition of matter and have a slightly different mass. But this is a complication I'm not going to go into. It has to do with relativity. But yes, we don't need to think about that. We don't need to take this reductionist view to define mass, whereas we would with this quantity of matter business. So now that we've got this idea of scale, let's think about a concept related to mass and often confused with mass, and that is weight.
Okay.
Let's take our 1 kilogram standard and let's suspend it from a spring. What are the forces that are at play here? If we look at this diagram, let's first imagine that there's no spring. Let's take the spring away.
Gravity.
We've taken the spring away. What's going to happen to this 1 kilogram mass?
That's gonna fall.
But more importantly, it's going to
Fall.
accelerate. And how fast is it going to accelerate?
At 10 meters per second.
About 10 meters per second. So, and it's a 1 kilogram mass, which means that there's a force, which we're going to call weight, which is equal to 1 kilogram times 10 meters per second squared, which is 10 newtons.
Okay.
Remember, 1 newton is 1 kilogram times 1 meter per second squared, so this is 10 newtons.
Okay.
Now let's put the spring back in. Where is the spring scale going to be? Where's the indicator? Well, remember here in the picture I put the indicator there. Looks like it's like 5 newtons or something. Where is the indicator going to be on this one? If this is 0 and this is 10. So, well, if we don't have the spring scale here, then we know there's a force of gravity which is going to accelerate this 1 kilogram block at 10 meters per second. So we can think of the force because of F, some of the forces. There's only one force acting on it, and that is gravity.
Yes.
And it's accelerating at 10 meters per second, thereby Newton's second law says that the force is equal to the mass times the acceleration. There's only one force because we've only identified one force, that's gravity here. So the sum of the forces is equal to a single force, which is this gravitational force, right?
Yes.
And the magnitude of that gravitational force is 1 kilogram times 10 meters per second, 10 newtons. And it's in the downward direction, so we now have a direction for it. So I draw an arrow representing this, right? And the magnitude of this arrow is 10 newtons.
Okay.
Now, let me suggest that the spring is going to be applying a force in the opposite direction. I'm going to call this F sub S, F of spring.
Okay.
It is pulling up on it because you've had a spring before. You know if you pull out on it, it's pulling you back, right?
Yes.
So if I attach the spring to your earlobe, you'd be like, ow, right? It's pulling my earlobe.
Yeah.
If I put a spring in your mouth and told you to bite down, it's going to be hard because the spring is pushing in the opposite direction that you're trying to stretch it.
Yep.
Okay? That's the thing with these springs. If you try to stretch it out, it's going to try to pull you back in. If you try to compress it, it's going to try to push you back out. That's Hooke's law. So we have now we've got another force here though. When I put the spring scale back in, I've introduced another force. So now I have two forces. And so what can I say? But is there any acceleration here? If I hang a 1 kilogram block from a spring scale on the ceiling, does it accelerate? We know that the sum of the forces should be equal to the mass times the acceleration, but the acceleration is 0, right? So the sum of the forces should be equal to 0. What's the sum of the forces? Well, we got to keep direction in mind here. If we call this the positive direction and this the negative direction, the sum of the forces is, well, I've got F sub S, which is in the positive direction, plus negative F sub W, right? Which I could just write it as minus F sub W, because that's in the opposite direction. Okay, and that's equal to 0. So that says that F sub S, the force of the spring force, right, is equal to F sub W, which is equal to 10 newtons. So this guy is going to read, its indicator will be right there, be pegged out at 10 newtons, because that's as far as I want with my scale. So here we've applied Newton's law to study this simple system of measuring a mass with a scale, a spring scale. And this is how we reason through it.
Okay.
Does that make sense?
Yeah.
Yes.
Okay. Let me just do real quick one example of force is a vector. Okay? I mean, force is a vector. And so let's imagine we've got a post. This is a stump. And we want to pull that stump out of the ground. I could have a tractor, right, which is pulling with some force 1 in this direction. And then another tractor, which is pulling with force 2 in this direction. And let's say that those directions are orthogonal, right? They're 90 degrees to each other. So F1 is pulling with a magnitude of, let's say that's 1 Newton due north. Use a compass. And the other tractor is set up to pull with 1 Newton due south. No, not south. Would be bad. Due east.
Okay.
What is the resultant force? Well, we can treat this. We've got, this is my 1 Newton in the eastern direction, and this is my 1 Newton in the northern direction. Should probably make it a little more equal. Then Pythagorean theorem, right, gives us the net force.
Yes.
And so that will be equal to the square root of 1 squared plus 1 squared, which equals the square root of 2 newtons. That's a terrible end for newtons.
All right.
So just like with velocities, we can do it the same way. We can even define the angle, right? So that's the magnitude of the force, but which direction is it going? Well, the angle, theta, so we know it's somewhere in this direction, but what is this angle? Right? Figure out what theta is. Well, theta is just equal to, the tangent of theta is equal to the opposite over the adjacent, which means that the angle theta is the arctangent of 1 divided by 1, which is just 1. Whose tangent is 1?
A 45 degrees.
45 degrees. 45 degrees, they're equal. And so when I divide them into each other, I get 1.
Yes.
So this angle is 45 degrees. So that's 45 degrees. And the force is the square root of 2 newtons.
Okay.
So I guess you'd call that square root of 2 newtons north by north, or northeast. Or due northeast? I'm not sure. I'm not a compass person, to be honest. So that's the vector nature of a force.
All right.
I want to conclude with just a couple more questions. Let's see. All right, so you see a car rounding a curve.
Okay.
Is there a force present?
Wait.
Car is going around a curve. Is there a
Yes.
force present?
Yes.
There must be, right?
Yes. Because there must be an acceleration.
There's an acceleration. It's changing its velocity, okay? If a force, a known force, call it F1, we know its magnitude and direction. If it acts on a body, and this is all the information you know, can you tell which direction the body will move?
Yes.
Really? Let me ask you the next question. If a known force, whose magnitude and direction I know, acts on a body that is initially at rest, can you tell which direction the body will move? Do you see the difference?
Yes.
So the body that's initially at rest, that means that all the forces are balanced out. If it's at rest, there's no acceleration. That doesn't mean there's no force. There could be a couple of forces that are balanced out, and therefore it's not accelerating.
Yeah.
But it's initially at rest. So if I apply a force that has a known magnitude and direction, I can tell which way the body's going to move, right? Because if this thing is initially at rest, whatever these forces might be that are all balanced out, and I apply some known force, F, it's going to move in the direction of the applied force. That's what Newton's law is telling us, Newton's second law.
Okay.
If I don't know about the state of the body, if I don't know that it's at rest, maybe it's accelerating. Well, if that's the case, then we would have to do a vector addition, like we just did, of all the forces involved to see which direction it's going to go.
Okay.
Does that make sense?
Yes.
Okay. So it gets a little complicated. Solving some problems, you'll begin to see how to do these things. We're going to do one more lecture, and it'll be on Newton's third law, because this is easily misunderstood, and we have to be very careful to apply it. Right? In the meantime, you might think about the following. You remember that Newton's third law says that for every force there's an equal and opposite force?
Yeah.
Well, if that's the case, then I have a horse pulling on a horse cart, but the horse cart, of course, is going to be pulling back on the horse, equal and opposite. How does the horse cart ever move? So give that a think, and we'll talk about it when we talk about Newton's third law in a little more detail
Okay.
in the next lecture lesson.